Overview. So we've got 4 topics here, or 4 sections, 7.1 through 7.4. This is test number 6. As always, you have 3 parts: multiple choice, short answer, and then free response. If you felt confident in the last few days about the classwork and the math problems and the problem set, even the lab yesterday, if you felt all right going through those problems, that's really the gist of the math from 7.3 and 7.4. 7.1 and 7.2, I want to spend a little bit of time today reviewing the math from that because of the idea that it was momentum impulse theory, and we did that before break. It was delta P equals Ft. All right, so let's start with that formula first. So 7.1 and 7.2, we had this formula, delta P equals Ft, and then simply P equals mv. These were the 2 formulas that we introduced in the beginning of this chapter. The one on the left here, tells us that when there's a change in momentum in any object, it must occur because of a force, some net force or some external force. And that force is applied over a given time period. The example of this, if you want to think about it, the easy thing to think is a shock absorber or the airbags, or remember we talked about when a gymnast lands, they would never land with flat or with locked knees. They would absorb the shock in their knees as they land, and therefore increasing the time period. Now remember that delta P is the change in an object's momentum. So the egg toss, the other example, whether or not we throw an egg or toss an egg to somebody, whether or not you catch it like this or you catch it like this, the same delta P occurs. It's got momentum beforehand, right? You toss it, it has velocity, so it has momentum to start. When it hits your hand and stops, it has no momentum. So delta P is some given value. Whether you catch it like this, by letting it smack into your hand, or you catch it with soft hands, delta P is not changing. It's the change in the object's momentum. It's the same thing for both scenarios. But in scenario 2, when I catch the egg with soft hands, I increase the time period of contact. And as a result, the force on the egg decreases. God bless you. The force on the egg decreases. So the example we did in class is we just chose numbers. We said, you know what? Let's say the object's change in momentum is simply 10. And if after 1 second you're able to cause it to stop, after 1 second you can cause it to stop, what would the force be? And obviously the force is just 10 in this case. But suddenly, if instead you make the time period of contact, say like 2.5 seconds by slowly catching it, now you've increased this value here. This is still 10 because the same egg is still slowing down. And 10 divided by 2.5 would give us a force of, instead, in this case, that should be a 10 here. Instead of 10 newtons, the force would be 4 newtons. So as the time period of contact increases from 1 to 2.5, the force felt decreases. How are they related? What's the word for that? You should know this by now. Indirectly. Very good. Okay, because if the time period goes up, you take longer to catch it, the force felt goes down. There are so many ways I can ask this problem with so many situations that are analogies to what I just gave you. For example, remember the question about the catcher's glove. That's exactly what a catcher's glove does. It slows down the ball in a given time period instead of it just obviously smacking into your hand. You say, yeah, there's padding and stuff in the glove. That is true. But what it's doing is it's slowing down the ball for a longer period of time and therefore decreasing the amount of force you feel. You could think about momentum impulse theory with a golf player. A golf player hits the ball with a certain amount of force. It's in contact with the ball for a certain amount of time. That's F and T. And you could find the change in momentum as a result. Okay, so these problems can really vary. Let's take a look at an example of that real quick. Let's take a look at an example where we have, let's say the problem says the following. You could type this or write this if you want so you could think about an example. The problem says the force acting on an object is 27 newtons. The force acting on an object is 27 newtons for a time period of 0.5 seconds. As a result, determine the change in momentum of the object. As a result, determine the change in momentum. So, change in momentum really means delta P. That's what you're trying to find. And if you recall, delta P simply equals F times T. So a problem such as this, where you're only given the force applied and the time period, when you're only given these 2 variables, you can still find the change in momentum by just simply plugging those 2 numbers in here. You don't have to be given the mass and the velocity to actually find the change in momentum. You could do it that way also, right? If I give you the mass of an object, the initial velocity, the final velocity, you can do final momentum minus initial momentum. You can do it this way. You could say, okay, you know what, this is final minus initial, and just determine this value, and that's the change in momentum. But if you're not given anything about the mass or the velocities, and you want to find the change in momentum, you could simply figure out what the impulse is by taking 27 times 0.5. That would give you the impulse. And remember that impulse equals the change in momentum. That's why it's called the momentum impulse theory. We did examples in class of this where I did give you a mass and a velocity and a force and all that information. And in that case, what you would do, this is something that you probably practiced last night with the problem set. In that case, what you would do here is you would have to say, okay, you know what, if you're given the mass and the velocities and the force and the time, and you're trying to find one of them, you need to plug in for delta P. So delta P again is PF minus PI, final minus initial. Final momentum is mVF, initial mVI equals FT. The reason I'm pointing this out right now is because after 7.3 and 7.4, so many students always want to go to the conservation theory, which works for a lot of problems. But for problems where you're given information about the force felt and the time period and the velocities, you're going to use this equation right here at the bottom. Okay? If you're given a final velocity and initial velocity, this is only for one mass. This is not for two masses. That's your key. You want to write that down. When only one mass is given, and there's only one object in the problem, you're going to use the momentum impulse theory. Because this involves just one mass. The mass and the velocity at the end, the same mass and the velocity at the beginning. When you're given two masses, what are you going to do? Most likely, if you're given two masses, what are you going to do? What formula or what section was that from, or what theory or what name, or what do we do with two masses when you're given? I did it last night. No. Yeah, so we can use the inelastic or elastic collisions from yesterday. When you're given two masses, whenever you're given two masses that are interacting, you have to think right away that's elastic or inelastic. Elastic or inelastic. Okay? Now, in a problem like this, what am I going to do? I'm going to give you all of the values except for one of them. But I might say something like it starts from rest. Or it starts and then it slows down and it ends at rest. Or it comes to rest is the saying, right? When you hear that, what do you automatically do? If you hear it comes to rest or it starts from rest or anything like that, what would you do? Gus?
MVI is 0.
Yeah, one of these two would be 0. If the object started from rest, this drops off. This just becomes 0. If the object comes to rest at the end of the problem, this is 0. Are we clear on that? Does that make sense? We need to know our key words. Those key words are big factors in the problem. Because if you forget to write down that when it comes to rest, that means v equals 0, you're not going to be able to solve the problem. You'd have too many variables missing. The second thing I'd like to point out in this, if I'm moving this way, okay, and somehow a force was applied to me to cause me to stop, which way does that force have to act? I'm moving this way and somehow I stop. Which way does it act? Point. Yeah, it's got to go that way. The only way to slow down motion of an object is to oppose the motion, right? So if I'm moving with a positive velocity, the force is then negative. Last night in the problem set, if you recall, you were looking at some of the examples, and one of them had a problem where the force was given to you. It said the magnitude of the force is, I think it was like 500 newtons or something. The magnitude of the force. But all you had to do in that problem was recognize that it was a negative force, because the velocity in the problem was given as positive. What if the velocity in the problem is negative? The force then acts positively. So what you'll notice is that the sign for these velocities will most likely be the opposite of the sign for the force. Okay? Again, if you're moving to the right, force has to push left. If you're moving left, the force has to push right. It's got to be the opposite of the velocity's direction. There's also an example we did where an object was thrown or kicked into the wall, it hit the wall, and it bounced back. And in that case, we said, you know what? What's the force exerted by the wall? Well, the first velocity was that way, right? VI. So that's a positive velocity. After it hits the wall, though, what kind of velocity do you have? Negative velocity, because it comes back off the wall. So you have to consider these things. The direction of the velocity is extremely important. It is extremely important. Is that clear? West means negative. East means positive. Left means negative. Right means positive. You can even switch the two. It doesn't matter, but you can't call them both positive. Can't call left and right both positive. Okay? That's the momentum impulse theory. Generally, I'm going to have Caroline talk in a minute, but before that, I want to make sure that we see that this formula up here is not ignored. Simply P equals mv is the basic formula to find the momentum of any object. So hey, there was a problem set question last night that said, is it possible for a baseball to have more momentum than a truck? What's the answer? I heard yes right away, and I see all you shaking yes. How is that possible? A truck is so much bigger than a baseball. Yeah, as long as the baseball has way more velocity than the truck to compensate for the lack of mass, it would. What's another reason?
What if the truck just wasn't moving at all?
Exactly. If a truck's not moving, what's its momentum? Zero. So if the ball is simply rolling very slowly, it has more momentum than the truck. And that's kind of weird to think about. It's different than inertia, right? Inertia is a measurement of mass. It's the desire to stay where it is. The truck definitely has more inertia. But momentum, the ball could have more momentum if the truck is not moving. That's another way. But either answer is acceptable there. Okay? We used this formula a couple of times, but then we really used this formula in 7.3 and 7.4. All of our equations in 7.3 and 7.4 had mv, right, all over the place because of the momentum involved. All right, let's pause for a quick second. We're going to take a look at an example, other examples. Well, first of all, what questions have you maybe had from the problem set last night? Yeah, feel free to take an image of this if you want. I know it wasn't in the recording, what we just did on the board. Yeah.
It was 81. It was something like when you kick a ball and it didn't even know like you're missing a variable, so I don't know.
Okay, so 81, I think it was about momentum impulse theory. Was it from section 1, 7.2? Where was number 81? 7.2? Yeah, okay. So this is the problem I was talking about before. The problem for number 81 gave you, ready? It gave you the force that you delivered, right, to the soccer ball, and it gave you the time period of contact with the soccer ball, those two things. And what did 81 ask you for? What does it actually say? What did it ask you for? Nobody have it in front? Anyone have the actual question? No? Some of you take screenshots, I thought, no? This is page, what, 270-ish? No, 260-ish. All right, here we go, I have it. It says, find the magnitude of the impulse delivered, okay? So first of all, from earlier we talked about this. Please remember, this is impulse. That's what impulse actually is. This is the change in momentum. That's why this is called the momentum impulse theory. The change in an object's momentum is equivalent to the impulse felt by that object, the impulse that the object feels. And in this problem, you were told that a force of 1,250 newtons, was applied to a soccer ball by your foot. You kicked it for a time period of 5.95 times 10 to the negative 3 seconds. So you're given the force, you're given the time, just multiply the two. That's the impulse delivered. Yeah. And that's why, remember I was saying earlier, you might not always be given the mass. So in this problem, you're given nothing about the mass. But the problem says, find the impulse. It's just F times T. Well, the answer you get for the impulse, that's the equivalent value of the change in momentum. We don't have the mass, we don't have the velocity, but by finding the impulse, you also know what the change in momentum is, because those two things are equal to one another. Okay? Yeah?
Can we use a question like this on the test?
Yeah, this would be very simple, though. This would probably not be a long answer question. This would probably be like multiple choice, and I'll make the force something like 2 newtons, and the time period a half a second. So the numbers are really simple, so it's not a really lengthy math problem. So if I gave you something like this, it could be either multiple choice or conceptual. It wouldn't be a math problem because it's really honestly not a lengthy problem. For the math problems, if you look back at 7.1 and 7.2, look at the notes. We did some examples where the velocity was given, the mass was given, the force was given, the time was given, and you had to find the final velocity. That would be the problem you would be using for math, where you would use this formula. Instead of using that for the formula, you would use this, right? Which converts to this. So for the math part of the test, this is really the formula you want to know for momentum impulse theory. Okay, this is what you're going to end up using for momentum impulse theory. All right, what else? I want to take questions because we've been doing so many problems. Like I could do more examples right now, math problems, but you guys did so many in the lab. You did them last night for the problem set. I feel like I'm just like drilling this into your head for no reason at this point. Like you've done it so much. Did you struggle on any of the problems last night? Any of the conceptual ones? Because I felt like a few of those were a little bit tricky.
There's the one who's space. I don't know.
Yeah, an astronaut is in space. Okay, yeah, that's a good one. So there was a question where the astronaut is in space and he's tethered to the space station with a rope. The rope suddenly snaps. And how many of you have seen Gravity, that movie with Sandra Bullock? Is that her name? Yeah. Okay, in Gravity, if you recall, there's one point in the movie where they take the oxygen tank, is it the oxygen tank or one part of it, and almost release it so it expels the air. By pushing that way, though, the person gets pushed backwards because of conservation. So let's explain that. Remember the two ice skaters at the center of the ring? If two ice skaters push off each other, which way do they each move? So if you're in space and there's nothing else affecting you, there's no gravity pulling you down, and you take this book and you throw it that way, you give the book positive momentum, don't you? How's that possible? How could you give it positive momentum? Because to start, if you're standing still, or if you're in space like this, what's your momentum right now? I'm not going to throw it. Your momentum is 0. And then you launch the object that way, giving it positive momentum. How could you give positive momentum when you started with 0? What do you have to have? Negative momentum. Because remember that if you start with 0 momentum, you have to end with 0 momentum. So if you give positive to the book, you have to have negative so that they balance out. So if you are stuck theoretically, like on an ice, you're on an ice rink or a lake or something, you're stuck somewhere and you need to move. And theoretically, this again, a lot of this is theoretically, right? In space, actually, though, this works perfectly. But on Earth, it'd be theoretically because there is friction. But if you're on frictionless ice and you only had shoes on, and you're like, oh, my feet are cold though. Well, you have clothes on too, but your shoes are on. You take your shoes off and you throw them that way. Theoretically, it would push you back to the shore of the lake. It wouldn't really work because there is friction on the ice, actually. It's not perfectly frictionless, but the concept makes sense, okay? If you've played hockey before, if you've been on ice skates, you push off the wall, you go backwards. Why doesn't the wall go forward? It's stuck to the ground. It's not a second object moving. If you push off the wall and go backwards, that's momentum impulse theory. The force you apply to the wall over a given time period equals the change in your momentum. That would push you back. Is that clear? You push the wall this way, which way does the wall push you? Back. Equal and opposite, right? Newton's third law. For every action, equal and opposite reaction. So if I push this way, the wall technically pushes me this way. The wall delivers a certain force that way for a given time period that I'm in contact. If I did this, if I was skating like this, am I going to move very far? But if I went like this and pushed off with the same force for a longer time, wouldn't I go pretty far? What am I increasing? What parameter, what variable am I increasing by pushing off like this versus going like that? Same, I'm assuming it's the same force. I said that before, sorry. So same force, say 100 newtons this way, 100 newtons this way, if I'm able to do that. What am I increasing? Time. I'm increasing time here. So by pushing off like this for a longer time period with the same force, I would have increased time, same force, therefore my increased momentum, my momentum would therefore increase. So by doing this, I'm able to generate a lot more velocity because it's increasing my momentum because of the increasing time that I'm pushing for. There are so many examples. Again, there are literally like an infinite amount of examples I can give you for the momentum impulse theory. Okay? It really, I mean, there's so many. A car thrust that way causes the momentum to change that way. I mean, it's so much that you could just come up with so many of them. But you need to recognize when there's a force applied in a time period and a change in momentum that you're using the momentum impulse theory. Okay? We had two equations from 7.3 and 7.4. I mean, really only one actually, but we then record this too. Okay, so this here shows us when, if we're looking for the mass, we can simply divide by the difference Vf minus Vi to get the mass by itself. So if you're trying to find the mass and you know that the final velocity of the object was 10 meters per second, it started with a velocity of 2 meters per second, so it's gaining velocity, right? It ended with more velocity than it started, so the force must be positive. So let's say the force was like 200 newtons over a time period of a half a second. You could find the mass. Okay? So yes, this formula here is the one that you really want to use for the math parts. But if you're looking for mass, you got to adapt. You got to take these two m's you see here and factor them out in front as a GCF. Okay? I'm going to go back to the other slide now. Kind of manipulate it a little bit. The first equation was when the objects collide and then separate, and we called that an elastic collision. And that occurred with this equation. First object times its velocity. Second object times its velocity before the collision equals first object times its velocity plus second object times its velocity. Do me a favor real quick, if anybody has it, pull up the formula sheet. Tell me, I think I give you this formula actually on there, on the formula sheet. Just tell me if it is or isn't before I actually say it's there. It is, right? And is the other one also given for elastic? Okay. So on the formula sheet, you're going to see 4 formulas. Momentum impulse theory, P equals mv. You'll see this formula right here. And then that's for elastic. And then for inelastic, you'll see this. Oops. Okay, and remember from your lab, why does this happen? What do the objects do after collision? They join together and fuse. Okay? So the idea here is that they're together afterward. Yeah?
Why would you use P equals MV?
Just that formula, you mean? If a problem said, we started the year with something like a bowling ball has this much mass and velocity. How much velocity must the bouncy ball have to have the same momentum? Or maybe in like a simple multiple choice, the velocity of an object triples, what happens to its momentum? Well, since they're directly related, it triples. The mass of an object doubles. What happens to the momentum? It doubles. They're they're directly related, everything there, right? Okay, so if mass increases or velocity increases, momentum increases by the same factor. Last test, God bless you, last test we had to focus on kinetic energy, remember? And when you doubled the velocity, you quadrupled the kinetic energy because it was v squared. Is it v squared anymore? No. It's P equals mv. So trooper, one of those kinds of questions with relationships, okay? In the first example, what did we say delta Ke is here for elastic? What would delta Ke end up being? Elastic.
0.
Yeah, no energy loss. Okay, here though, this is some number. Okay, this is some number. And what kind of a number are you going to most likely get? A negative number. Because you're losing energy in an inelastic collision. Yes? I'm going to most likely give you a problem on the test, right? And then afterward just ask you, was it an inelastic or elastic collision? And to answer that, you have to find delta Ke as a result. Okay? That's my hint. It would be something like that. Or maybe I would even say it's an inelastic collision, and part B would be find the energy loss due to the deformation. Literally what we did yesterday in class with the 2 train cars colliding. There's no other way to ask these questions. Do you see that? Whether it's 2 train cars, 2 cars, 2 desks, 2 football players, it doesn't matter. It's the same situation every time. Either they hit and separate, or they hit and stay together. That's it. There's no other way to ask these questions. So what you need to really make sure you're doing is you're practicing. That's it. You have to practice with this topic. It's not going to get any more difficult on the test than it's been in class, is what I'm saying. There's no other ways to ask these. You just have to sit there and practice problems and break them down. The hardest part is doing what usually with these problems? What do you think the hardest part for these problems is? The math is really simple.
Writing out the period.
Yeah, knowing what each variable is, the givens, and knowing which equation to use. What are the givens? What equation do you use? That's the hardest part. You know what I see mistakes most on tests? I'll tell you right now. Mistakes with subscripts. Some students write a subscript down and then carry it down wrong because there's all these 2F and 2I and 1I and 1F. So if the subscripts are really bothering you, don't call them object 1 and 2. If it's like 2 trucks, call them a truck and something else. Could use the letter T and something else. Because I see in some of your work, the 1 and the I look similar. And I do see a lot of mistakes with that. I know it sounds ridiculous, but maybe call them object A and B instead of 1 and 2. Okay? I'm trying to think of other examples I could possibly give you on this. Others from the problem set? Any other questions? Questions from the lab right now? Because that'd be a great thing to use as a review to also ask. Any questions from the lab? Even the later questions, there were like 2 pages of questions. I have to give you the lab. There were 2 pages of questions at the end there. Hopefully tonight you'll finish that up and bring that in tomorrow. Okay, you have 7-4 tonight also, but honestly, I'd probably do the lab. I won't count 7-4 late if you turn it in over the weekend. I'll make you that deal. It's fine. Okay, if you turn it over the weekend at some point, I'll count 7-4 as on time. But if you really want to practice more, the examples from 7-4 are good examples to use from the homework. Okay? I'll push the homework for like Sunday night instead. Yeah?
Wait, so what type of question again would you ask in momentum impulse theory?
So, a momentum impulse theory question, you would be given something about the object's motion, either before or after the force is applied, and you'd be given the force in the time period. Or, you'd be given the object's motion, right, to start, the velocity and mass. You'd be given the object's velocity and mass to end, and then maybe I give you the force, and you have to determine how long does that force act in the time. So really, Gus, is all you're doing, if you go back, I'll pause and go back. Other questions? Other things you're concerning? Got about 3 or 4 minutes though. Yeah?
The physical quantity that is not conserved in an elastic collision.
Okay. So it says, let's talk about things that are conserved or not conserved in an elastic collision. In any collision, you always have momentum conserved. Always, right? Momentum is conserved whether it's elastic or inelastic. But what is or isn't conserved in the other sense is kinetic energy. So for an elastic collision, the kinetic energy is conserved, which means there's no change in kinetic energy. But for an inelastic collision, there is a change in kinetic energy. You lose some kinetic energy. Usually this is a negative quantity, so kinetic energy is not conserved. Okay? It's not conserved in an inelastic collision. But momentum is always conserved. Momentum is always conserved. Really not much more. I could do an example real quick, I guess. How about this one? This is a little bit of interpretation you have to figure out. 2 objects are moving to the right together with a velocity of 5 meters per second. 2 objects. Their masses are 5 kilograms and 3 kilograms respectively. They're moving together to start. When I say that they're moving together, what does that automatically make you think? The masses are together and there's only one velocity. So this kind of a problem would start like this. It'd be the opposite of the elastic collision we keep talking about. If they start moving together with what did I say the velocity was?
5.
Okay? And as they're moving together, suddenly an explosion occurs and one object launches to the right and one object launches to the left. This is like the truck example with the steel beam in the back, where the steel beam falls out the back of the truck. Okay, if they separate afterward, you have this. Okay? So look at the truck example if you want to look at one where there's a separation after they're moving together. You need to adapt on the test. That's the key here, okay? The equations aren't changing. Today after school,